Hey, welcome to The Explainer. Today, we're going to take a journey into the hidden tech that makes our digital world feel, well, instant. We're talking about distributed caching. It's the invisible magic that powers pretty much everything, from a viral video to your social media feed. So let's dive in.
So, have you ever wondered about this? How is it even possible for a video to drop and, within seconds, be watched by millions of people at the exact same time, with zero lag? The answer isn't magic. It's actually just a really clever piece of system architecture.
Okay, so the secret lies in this pyramid right here. Every computer system has to deal with a constant trade-off. Down at the bottom, you've got massive, slow storage. Think of a hard drive. It can hold tons of data, but it's slow to get to. Then, way up at the top, you have super fast memory, like RAM, but it's much smaller and way more expensive. That huge gap between fast and slow creates a major performance bottleneck, and that's exactly where caching comes in to bridge the divide.
So how do we actually bridge that massive speed gap? Well, we use caching. You can think of it as a small, super fast pit stop for data. It keeps a copy of the stuff you're most likely to need right there, ready for lightning-fast access.
This diagram here shows the most common way to do it. It's called cache aside. Let's just follow the flow. Your app first looks for data in the fast cache. If it's not there, and we call that a cache miss, it has to take that long, slow trip all the way to the database to get it. But here's the clever part. On the way back, it drops a copy of that data into the cache. So the next time anyone asks for it, bam, it's right there, ready to go.
So really, it all just boils down to this. A cache hit is awesome. It means a super fast response. A cache miss is slow. It means a long trip to the database. The entire game for system designers is to maximize the number of hits and minimize the misses. It's that simple and, well, also that complex.
But this brings us to our first really big problem. Remember, that fast cache is small and expensive. It's prime real estate. Sooner or later, it's going to fill up. What do you do then?
Yeah, this is the critical question. The cache is full. To add something new, you have to get rid of something old. But how do you decide what gets the boot? You can't just pick something at random, right? That would be totally inefficient. To solve this, a system needs a set of rules. We call it a cache eviction policy. And the most popular one by far is called LRU, which stands for least recently used. And it's pretty much as simple as it sounds. You just throw out the thing you haven't touched in the longest time. You know what? To make this crystal clear, let's just forget about servers for a second. Let's think about your clothes closet at home. Now, this closet has a fixed size. Let's just say you only have 10 hangers. That's it. This represents that limited, expensive space you have in your cache.
Okay, so you go out and buy a cool new shirt. You want to put it in your closet, but all 10 hangers are already taken. What do you do?
Well, the choice is pretty logical, isn't it? You look for that one shirt that's been hiding in the back, the one you haven't worn in ages. You take that one out to make room for the new one. And that simple decision, right there, that is the least recently used algorithm in action. Now, that closet metaphor works perfectly for a single computer. But what happens when you're operating at internet scale, with thousands of servers all trying to work together? That simple closet, it becomes a massive, chaotic warehouse. And whole new, much scarier problems start to pop up. This is where we run into a scenario with a terrifying name. A cache stampede, or a thundering herd. Imagine that viral video from earlier finally expires from the cache. In the very same millisecond, 10,000 people all get a cache miss, and their requests slam into the database all at once. The database just can't handle it. It gets overloaded, the whole system grinds to a halt, and suddenly nobody can watch the video. That's a thundering herd. And this image here shows one of the classic ways a stampede can start. In a big system, use something called a hashing algorithm. Think of it like a digital sorting hat to decide which server stores which piece of data. Now, with a simple, kind of naive algorithm, if just one server goes down for maintenance, the whole sorting system breaks. Almost every piece of data gets a new assignment, nobody can find anything, and you get a massive system-wide storm of cache misses.
So, to prevent that chaos, engineers came up with a really elegant solution called consistent hashing. Instead of thinking of servers as a fragile line that's easy to break, they imagine them arranged on an abstract circle, or what they call a hash ring. And you can really see the difference here. On the left, you've got that fragile line where knocking out one block causes a total reshuffle. But on the right, with the hash ring, when you take out a server, only its immediate neighbors are affected. The vast majority of the data stays exactly where it is. It's a much more resilient, stable system that helps prevent that stampede. So all these challenges lead us to a fundamental, high-level truth about building large systems. There are no perfect solutions. There are only very deliberate, conscious trade-offs.
And this brings us to a foundational principle in computer science called the CAP theorem. You can think of it as a non-negotiable law of physics that every single architect building a distributed system has to live by.
The theorem says that any distributed system can only guarantee two of these three things at the same time. First is consistency, meaning everyone sees the exact same, most up-to-date data. Second is availability, meaning the system is always online and responds to requests. And third is partition tolerance, meaning it keeps working even if parts of the network fail. You get to pick two, but you can never ever have all three. A bank, for example, will always choose consistency over availability. You'd rather see an error than the wrong account balance. But a social media feed, it'll choose availability, because you'd much rather see slightly old posts than nothing at all.
So you see, building these massive instant systems we rely on every day is a constant balancing act. To get that incredible speed and reliability we all just expect, architects have to make some really tough choices. Which brings us to the final question I want to leave you with. In that trade-off between having perfect, up-to-the-millisecond data versus having a system that's always on, what are you willing to give up?